Hello and welcome to this fourth video on the subject of high-frequency electronic design with Microwave Office. Today I'd like to talk about directional couplers and 90-degree hybrid couplers. You may remember we said a bit about hybrids in the last video, but I deferred the subject of 90-degree hybrids till now. Most 90-degree hybrids derive from directional couplers, the exception being the branch line coupler, which we talked about in the last video. So it's logical to begin with directional couplers and then go on to 90-degree hybrids, or at least the ones based on coupled lines. So that's what we're going to do today, and let's go to the computer. Okay, let's say we have two transmission lines that are close to each other. I think it will come as no surprise that if I excite, say, port 1, and have a wave on this line, some of the energy of that wave will be coupled to this other line. What may be a little bit more of a surprise is that if I do things just right, I can have all these ports matched. I'll get the amount of coupling to this other line that I want. And the really odd thing is that the wave on this line will be coupled in the opposite direction. That is, port 4 will be the output, port 2 will be isolated, and port 3 will get whatever energy is not coupled to port 4. For that reason, this is sometimes called a backward wave directional coupler. And it is, of course, directional because it depends on the direction of the wave. Now, the big question is, how do you analyze something like this? Well, if you just try to analyze these two coupled lines, you've got kind of a sticky electromagnetic problem. Electromagnetic simulator could certainly handle it, but back in the days when people first started talking about this kind of thing, there were no electromagnetic simulators. So we use even an odd mode analysis. Now, I introduced this earlier in one of the previous videos, but I'll just say briefly what's going on here. We can break this excitation down to these two excitations. This we call an even mode analysis, V over 2 at each port with the same polarity, same phase. And in this other circuit, we have the same thing except opposite phases here. This one's 180 degrees out of phase. Now, from linearity, we know that the response to this circuit, the one we want the response to, is the sum of these two responses. And that's because the excitation is the sum of these two excitations. So if we sum these two, we'll get this excitation. If we sum these two responses, we'll get the response of this circuit. That's even an odd mode analysis. Now you can see pretty easily that we've made things a lot simpler, right? Because this line and this line are the same. You only have to analyze one of these. And when we do, that's called the even mode impedance, even mode characteristic impedance. Down here, we have the odd mode. So this is the odd mode characteristic impedance. Now, analyzing that is an electromagnetic problem, of course, but it's a much, much easier problem than trying to analyze something like this in one fell swoop. I will also point out that the even mode characteristic impedance is a characteristic impedance of one of these lines when excited in the even mode. You just take into account one line. And similarly, the odd mode characteristic impedance is the impedance of one of these lines. From this, it turns out you can also get propagation constants and everything you need to know. Anyway, from the standpoint of designing one of these things, you end up with two very simple equations, which I'm showing here. K is the voltage coupling factor, not the power coupling factor. So for example, if you want a 3 dB coupler, K is not 0.5, it's a square root of 0.5, which of course is 0.707. Z0E, Z0O are of course the even and odd mode characteristic impedances respectively. The terminating impedance, Z0, is just a geometric mean of those two impedances defined this way. And typically what you want is to find the even odd mode impedances given K and Z0, but it's a simple matter to solve these things, of course. Now, once you've analyzed these coupled lines and you have the even and odd mode characteristic impedances, the even and odd mode phase velocities, which by the way are not necessarily going to be the same, you then can get a Y matrix for the set of coupled lines. And if you're doing computer circuit analysis, that's really as far as you need to go, because internally everything is in Y matrices. It's not in S matrices at all. But of course, then once you have the Y matrices, you can convert those to whatever you want: S matrices, Z matrices, H or G matrices, if for some reason you want those, but you can do it. If you want more on this, I will refer you to my most recent book on practical microwave circuits. It's covers all that stuff in a fair amount of detail, not the electromagnetics, but the circuit theory of it. Now, let's say we've designed our directional coupler using those terribly complicated equations that I showed you a second ago, and there's still a few things we need to be aware of. Three quantities in particular. Coupling is kind of obvious. That's the difference between the power at the coupled port and the available power at the input port. So for example, if we excite port 1, the coupling is the power to port 4 divided by available power at port 1. That's pretty easy to figure out. Two other quantities that are important are the directivity and the isolation. The directivity is the difference between the power coupled to the isolated port and the power coupled to the port that you wanted it coupled to, which in this case is port 4, assuming you're exciting port 1. Why do you have imperfect directivity? Well, it's mainly because perfection is kind of hard to come by. But there are two things primarily that will affect the directivity. One is the VSWR of this interface. So if we couple a wave to this port and there's reflections, they're primarily going to end up over here in port 2. So the directivity will be very closely related to the return loss at port 4. Not exactly though, because there's another factor which can affect it, and that is the difference between the even and odd mode phase velocities of the waves on the lines. As I said a minute ago, the even and odd mode phase velocities will not necessarily be the same. And in a microstrip medium, they will not be the same for sure. In a strip line medium, where both of these strips are fully encased in dielectric, they'll be very close to being the same, theoretically the same. But this is one of the things you have to watch out for in directional couplers. Generally, the weaker the coupling, the worse the directivity will be for that reason. Now, the last quantity is the isolation, which is simply the power at port 2 compared to the power at port 1. So you can see right away that the coupling plus the directivity is equal to the isolation, in dB, of course. Finally, we have some loss through the coupler between the input port and this third port, which we sometimes call the through port. And that's simply because some of the power is coupled off to port 4, and what's left goes to port 3. So if you look at it for 2 or 3 seconds, you'll see this is a relationship for the coupler's minimum loss. And of course, there are resistive losses as well, which will increase this somewhat. In any decent, well-designed coupler, there will, of course, be minimal. Now, I said earlier that the even and odd mode phase velocities in a microstrip coupler are responsible for rather poor directivity, especially in weakly coupled lines. So what do we do about that? Well, here's one trick that is performed from time to time. Here's a coupler, and you can see that the edges of the two strips are sawtoothed. This creates a slow wave structure between the lines, which affects the odd mode more than even mode, because remember, the odd mode is mostly between these two strips. The even mode is carried more through the dielectric that's underneath the strips, and that's why the even mode generally has a slower phase velocity than the odd mode. So the trick here is to slow down the odd mode. This sawtooth arrangement is a classical slow wave structure. The only problem with it is trying to design this is no longer straightforward. So how do you make one of these? Well, unfortunately, it's largely an exercise in cutting and trying. I think what I would do, and I hasten to point out that I've never done this before, is that I would try to make the length of this path such that the total phase delay for the even mode and for the odd mode through this coupler are the same. And the gap is correct for the coupling. That will not be exact, probably not by a long shot, but it's a place to start. And then you can rev up your trusty EM simulator and fine tune it. Now, what about 90-degree hybrid couplers? Well, I suspect you've probably anticipated by now that a 90-degree hybrid is simply going to be a directional coupler, which is designed for 3 dB coupling. That means you'll get 3 dB down at port 4, and it will be 3 dB down at port 3 because half the power has gone out port 4. I should also have mentioned an interesting characteristic of this coupled line directional couplers. The phase difference between port 4 and port 3, for all couplings by the way, is always 90 degrees. And it's 90 degrees from DC to light, not just at the center frequency. It's an interesting property. The problem, however, is that if you plug the numbers for 3 dB into the equations I showed you a little while ago, you'll find that the even mode characteristic impedance that you need here is about 121 ohms, and the odd mode is about 21 ohms. And it turns out that there is no way on God's green earth that you can possibly get those values in microstrip on any kind of substrate, high, low, dielectric constant, whatever, with 2 strips. So what do? Well, one simple solution is to take these strips and split them in 2. Up here, you'll notice we only have one set of edges adjacent, which limits the capacitance you can get between these strips. If we configure them this way, we now have 1, 2, 3 sets of edges that are adjacent, so there's going to be a lot more coupling. And it turns out that in most cases, with most substrates, you can achieve those even and odd mode impedances with 4 strips like this. Occasionally on very low dielectric constant substrates, things like fused silica, which is I think around 3.8, you will find that you may need 6 strips. But it's just the same game. You just take these strips and split them into 3, split each of them into 3 instead of splitting them into 2, and you hook them up the same way. Now the last part of the problem is for a lot of the applications of this type of coupler, you really want the outputs to be on the same side. So you want port 4 and port 3 to be on the same side of the structure. Unfortunately, as you can see here, they're not. So what do you do about that? Well, one thing you can do is to cut one of these strips in half, this lower one for example, and move it up here. Then of course you have to connect them all together with bond wires like this. And now your port 3 and port 4 are on the same side of the structure. That turns out to be a very practical thing to do. Of course, you now have the parasitics associated with the bond wires, not just in the center here, but at the edges. And those will limit the performance to a greater or lesser degree. But it turns out when you actually try to realize one of these couplers, these strips become very narrow. And the gaps also become very narrow. So it's very likely that these are going to be fairly long, since they're a quarter wavelength long, and they're going to be very thin. So the length of these bond wires is really not very great. And of course that means the parasitics they introduce are also not going to be very great. That structure is called a Lange coupler, or sometimes people say a Lange coupler. It was invented by a gentleman named Julius Lange, or Lange. Frankly, I suspect he probably pronounced his name something like Lange, but I'm not sure about that. I'm sure somebody will correct me though. Okay, let's go to Microwave Office and design a coupler. Again, I'm going to use the component synthesis wizard. I will select a coupler, simple coupler, single section. You can make multi-section couplers, by the way. I didn't mention that, but it's something you can experiment with on your own, I think. So let's just pick 10 gigahertz as a center frequency and 10 dB coupling, typical values. I'll pick an alumina substrate with the default settings, and then I can hit synthesize, go back to the component specs, and then you see I've got the even and odd mode impedances showing right here. Those are perfectly reasonable, realizable values, so we'll take them and send it to Microwave Office. Okay, so here's our coupler. Not much to show there. It is microstrip, conventional microstrip substrate, and we can analyze it. And here's our performance. This first plot is a through loss, which is about half a dB. And since you're losing 10% of the power in coupling, that's about what you would expect. The coupling is right on 10 dB, as you might expect as well. The third graph is the isolation, which is about 20 dB. And the input return loss is very nice. It's around 30 dB, but of course that doesn't include the effect of any input discontinuities, which you will invariably have. Note also that the isolation is 20 dB. At first that looks good, but the coupling is 10 dB. So that means the directivity is only 10 dB, which is not really great, frankly, but this is what you end up with weak coupling and a microstrip coupler. Okay, that was fun. Now let's try a multi-strip coupler. Again, with the component synthesis wizard, we have a selection for Lange hybrid, and we'll keep the same center frequency and everything. You can specify the fractional bandwidth. Since this type of coupler generally has a pretty good bandwidth, I'm going to make it 0.5. And let's go to microstrip. We'll have it alumina. And synthesize it into Microwave Office. Okay, and if we run the analysis, you'll see what we have. Okay. So these are the two couplings, the two outputs. If it were a coupler, these would be the through and the coupled ports. Since it's 3 dB, they should be at the same level. And as you can see, they are, believe it or not, 3 dB. This is our input return loss at 22, 23 dB. That's not bad. And this is our isolation, which is down around 25 dB. So this gives us a directivity of something like 22 dB. As you can see, with a tighter coupling, it's much better than with the 10 dB coupler. And that is typically what you'll see in microstrip couplers of all kinds. Now you notice that I could specify the bandwidth here. That's not really the same thing as specifying the bandwidth of something like a filter or a multi-section coupler, which is built around a Chebyshev characteristic, or God help you, a Butterworth characteristic. That is done so that if you want a little more bandwidth, it will actually overcouple at the center of the band so that the edges, the imbalance at the band edges will not be so bad. That's all that does. And it's not a bad practice also. And you can see why it's not really perfect. There's a lot of discontinuities here in the connections, and these blocks are actually bond wire models, and so on. There's bends. None of these are great models, but again, there's things you can do about it. I like to EM simulate the bond wires in the center and at the edges, and the whole structure at each end of the coupler. The models themselves for the coupled lines are very good. You don't have to worry about those. And if you do it this way, you can adjust the length with the tuner without having to change anything at the end. And that's a useful thing to be able to do also. Now lastly, I wanted to talk about the coupled line models in Microwave Office a little bit. If you go to microstrip, coupled lines, you'll see a whole collection of things. It's a little daunting, really. The important things to know, however, at least to get started with this, are the following. There's an element here called MCLin, which is your basic coupled line model. Here it is. Found it finally. This is your basic coupled line model. So when you're making microstrip directional couplers, which is two ordinary coupled lines, this is the one you'll use most of the time. Note that it's a closed form model, but it's still a very good model. Now for multiple coupled lines, see we have these things like M3, M4, and so forth. These are edge-coupled microstrip lines using a quasi-static electromagnetic model. That's a very accurate model, and it's also very versatile because it'll allow you to do things like have lines on different layers of a multi-layer substrate. And those are these GM 1, 2, 3, 4 lines. GM2 CLIN, for example, GM4, GM6, these can be on multiple layers of the substrate, and they can be any width, any spacing, they can be asymmetrical, whatever you want. So those are very useful for many kinds of things too, like making balance. These are a lot more useful than you might think at first. They're extremely powerful, they're extremely useful in all kinds of monolithic and hybrid circuit design. You may remember that I used some of these to show you how you can make a planar Marchand balun. And that is one of the few ways to make a good balun on a high-frequency integrated circuit. And there are other applications as well. They're limited only by your imagination, as in all things. And that's all I'm going to say for now about passive components. Now I would like to turn to some other things, primarily nonlinear analysis with Microwave Office, and how you set up problems in designing mixers and amplifiers and frequency multipliers and that kind of thing, so that they're analyzed efficiently and accurately.